Hi and welcome to today's video. In this video I'm going to be talking about enthalpy, and in particular we're going to cover two key ideas. We're going to look at the difference between endo and exothermic reactions. Now this is really a recap from NCEA level 2, and we're going to look at different types of enthalpy and different types. First, just a recap on endo and exothermic reactions. Okay, in an endothermic reaction, the energy of the products is greater than the energy of the reactants. So energy is being gained by the system from the surroundings, which means that the surroundings get colder because they are losing energy. So examples of this, any process that involves bond breaking, which includes changes of state, such as melting, boiling, and sublimation. Exothermic reactions, on the other hand, are ones where the energy of the products is less than the product energy of the reactants. This means that energy from the system is being lost to the surroundings. The surroundings are gaining energy, which means they get hotter. And so any bond forming process is going to be an exothermic reaction. So this is things like combustion is always exothermic. The first time you find me a cold combustion reaction, please do let me know. And things like condensation and freezing. Okay, so we talk about enthalpy, and enthalpy, which is given the chemical symbol or the mathematical symbol H, is the heat content of the reactants or products in a reaction. And more precisely, we talk about change in enthalpy, or delta H, which is the change in heat content. So if delta H is positive, then the system has gained energy, it's an endothermic reaction. If delta H is negative, then heat energy has been lost from the system. So that process is what we call an exothermic process. Now, in year 12, we just talked about change in enthalpy, and you might be familiar with that. What we're going to talk about this year is change in enthalpy from some very specific reaction processes. Okay, so we have 6 different processes that we talk about. Now, delta RH is just the enthalpy of any reaction. That's pretty much what we dealt with last year. This year we also have delta fuse H, delta vape H, and delta sub H, which are to do with state changes. So going from a solid to a liquid, that's fusion, a liquid to a gas, which is vaporization, or a solid to a gas, which is sublimation. Now the reverse processes are, of course, exothermic. They are exactly the same value for delta H, but the reverse sign. That's important to remember. The other two that we talk about are the standard enthalpy of combustion and the standard enthalpy of formation. And both these have a lot of applications in different calculations as we go through them. So I'm going to spend a little bit of time with those. Okay, first one though, fusion, vaporization, and sublimation are simply the heat change or the energy requirements for 1 mole of a substance to change state. All of these processes are endothermic, and sublimation requires the greatest amount of energy compared with vaporization or fusion, simply because you're breaking more bonds. So the more bonds you have to break, the higher the energy they have to be. Therefore, the greater the delta H value is going to be. Of course, that's for a given substance. So for example, water. Melting water requires less energy than boiling water, which requires less energy than subliming water. That's all this is. You can almost think of these enthalpy change values as a proxy for melting or boiling point. Okay? Because it's kind of melting and boiling point is the temperature that the system has to be at for that to happen. The enthalpy is the amount of heat energy that you have to put in to get it to that temperature. And sometimes you'll be asked to write equations for these processes, and they are very simple. But the most important thing is to remember to include the states of the substance, solid, liquid, or gas. And it's really, really important to include states when we start talking about some of these reactions. Okay, now the two that are quite different to anything you've come across before are the standard enthalpy of combustion and the standard enthalpy of formation. Now, combustion first. there's a couple of things to note. The first one is that little circle, like a degree sign, to the top right of the H. And that means that this is happening in standard conditions. So 1 mole of substance, 25 degrees Celsius, 1 atmosphere of pressure, everything in its standard states. Okay, so the enthalpy of combustion is defined as the enthalpy change when 1 mole of substance is completely burned in oxygen with all reactants and products in their standard states. And you will, not might, will, be expected to write an equation for the standard enthalpy of combustion for something as part of your exam. Okay, so you need to be able to recognize it, and you need to be able to turn it simply from a statement into a chemical equation. So for example, if we consider the enthalpy of combustion of ethane, fuels are fairly commonly used for these sorts of processes. So we're talking about combustion. We've got to be in standard state, so ethane is a gas at room temperature. For some obvious things, you should be expected to know what state it would be in room temperature. For some substances, if it's not clear, you would be given the state. Methane is a gas at room temperature. So it's combusting, which means it's burning. And that means, effectively, we're talking about a reaction with oxygen. Okay, oxygen, of course, is a gas at room temperature, and it exists as O2 gas, not single oxygen atoms. When oxygen combusts with ethane, the products of complete combustion, and you would be expected to know these, are carbon dioxide and water. There's the basic equation, but it is not yet balanced, so being able to balance it is also important. Okay, so we've got 2 carbons on the left-hand side in ethane, so we're going to need 2 carbon dioxides. We've got 6 hydrogens, which means we're going to need 3 waters. Always leave the oxygens till last, because actually oxygen can be quite variable. And because there's oxygen in lots of stuff, it's sort of the most complicated one to deal with. So we end up balancing that up. Now you will notice that there are 3.5 oxygens. Now normally when you would be balancing equations, your chemistry teacher, or me, has probably told you that halves are an absolute no-no in balanced chemical equations. The only exceptions to that, and like chemistry, there's always an exception to every rule. The exceptions are for these combustion and formation reactions, because the definition of the reaction is the energy required to completely combust 1 mole of substance, so 1 mole of ethane. Okay, and when you get given this information, usually you would be given some data, so you'd have an enthalpy value. In this case, it's negative 1,557 kilojoules per mole. And the enthalpy of combustion will always be a negative number because combustion is an exothermic process. Okay, so please do practice some of these. It's the same thing every time. You take the substance, you add oxygen, you produce carbon dioxide and water, and then you balance it. And yes, you can have halves. Okay. The enthalpy of formation is potentially even more odd, and it is defined as the enthalpy change when 1 mole of substance is formed from its elements with all reactants and products in their standard states. So you need to be at least a little bit aware of what the state of an element is at room temperature. Okay, again, these are in standard conditions because it's got that little circle there. And it happens at 25 degrees C and 1 atmosphere of pressure. Now, if you think very carefully, any pure element, such as oxygen gas or hydrogen gas or anything like that, that's going to have an enthalpy of formation that is 0, because it's defined as the enthalpy required to form it from its elements. And if it's already an element, then you can't form it from anything else. So it's nothing. Okay, so what does this look like? Well, let's say we've been asked to write an equation for the enthalpy of formation of ethanol. Again, this is not particularly uncommon. So first thing you're going to think, we are making ethanol. That means ethanol is our product. We should have a state in there, and hopefully most of you are aware by now that ethanol is a liquid at room temperature. So remember the definition. We are forming 1 mole of this substance from its elements in their standard state. So what are the elements that make up ethanol? Well, to start with, we've got carbon. And at room temperature, carbon is a solid. We don't have a formula for carbon, so we're just going to call it carbon. Okay, what else have we got in there? Well, we've got hydrogen. Hopefully you're aware of the fact that at room temperature, hydrogen is a gas and exists as H2. And of course, because I've got 6 hydrogens in my ethanol, I need 6 hydrogens in my reactant, so 3 H2s. And the last element that's present in ethanol is oxygen, which of course also exists as a gas at room temperature as O2. So that is how I would write the enthalpy of formation for any substance. So you're breaking it down to what are the elements that make this thing up, what are their states, and then just balancing it off. Again, just like with combustion, we're allowed halves in these equations, just because. Okay, that's not normal, I know, but it is for these reactions. I hope you found this useful. Please do go and practice these. But more importantly, when we come to Hess's law calculations especially, you will have to write these equations. So please know how to do it. Sometimes there might be an achieved exam question that requires this, but most of the time it's in part of an extended question. All right, hopefully I'll see you in the next video and you'll find this useful. Bye.